back to Bytes of Pi. We're going to cover the second part of recursion. If you remember, in last video we talked about summing up, using recursion to sum up numbers from 1 to n. We noticed that it would be easier just because we can use recursion to solve the problem where the number is 1 plus the sum of all the rest of the numbers. It's a lot easier to do this iteratively. It's easy for me to use a loop and say while counter is less than n, or in this, say 10, keep incrementing the number that you add and sum it all up rather than calling it the function itself. In Lab 8D we talk about Fibonacci. You'll discover that recursion has the overhead of multiple method invocations. You'll see that the larger the Fibonacci sequence goes, the longer it takes a computer to figure it out, because it keeps stacking the same method over and over again. And I know on my computer around 42, Fibonacci 42, the program will not return because it just stacks up so much and uses up so much memory that it won't return anymore. But if I did it iteratively, it comes back within milliseconds. You need to be able to determine when recursion is the best technique to use. Another thing we need to talk about is indirect recursion. Up till now we've been talking about direct recursion, where the method calls itself. Essentially you start off with a base case. Once you hit a base case you return immediately. Otherwise you do some sort of algorithm and call itself until you hit the base case. Now you always have to make sure you hit the base case. Indirect recursion is where you don't necessarily call yourself. You could call a function, another function, which then calls yourself, or do that 3 or 4 times. Like for example, I call a function called start, and it calls another function called next, and somehow next calls start again. So indirect recursion is where where you end up looping and you end up calling the methods over and over again, but you don't call the method directly, you call it indirectly. This is called indirect recursion, and it's a lot more difficult to trace. Some of the functions we'll get into later will have some indirect recursion. So I tried to figure out what the best way was to demonstrate recursion, and one of the coolest things is using Lightbot. I won't go into the details here, but here's an example where I could use indirect recursion. I won't go to the details of Lightbot, but essentially I have a main function where I call, I have 2 methods here where I can put in commands to this bot. Essentially my goal is to light up all these blue squares by commanding the bot where to go. So I will start off by calling this first method. And here in the method I'm going to light the square I'm standing on, jump down, light that square. Oops, I need to probably, here we go, start the clock here. Okay, there we go. So light the one I'm standing on, jump down, light that one, go forward, light that one, go forward, light that one again. Then I'm going to call P2. So I've just lit up all of the blocks right here up to this square. Now in P2 I'm going to jump up, I'm going to turn a quarter turn to the left, and then I'm going to call P1 again. So essentially I'm calling this method, which will go do all these commands, call this method, which will do these commands, and then call P1 again. This may go a little fast, but you can follow it and see how I can use looping to cover all these squares with the least amount of commands. Let's have some mood music and give it a try. And follow it, you see it's going here. Now it'll hit P2, goes back to P1, and starts the process over again. So you see a kind of pattern here. You light up a pattern, it turns the pattern again, and calls itself again. So here you can see indirect recursion, where I'm calling procedure 1, which calls procedure 2, which calls procedure 1, and continues the process all the way till its completion. So that's a tangible way of doing indirect recursion. Now another more complex form. We've done very simple recursion up till now. We're going to cover a little more complex recursion called maze traversal. Now I was like, what's a good real-world example of recursion? And you guessed it, Google Maps. So essentially, have you ever used Google Maps to trace where you're going? Well, how does Google Maps know what the shortest route is? Well, it probably uses a recursive function. You have your starting point, and it'll take every road or highway, it'll probably defer to highways as they are faster, and then to back roads as slower ways. But they'll keep doing this path traversal. They'll try going the path this way, and if it finds a faster path, if it finds a slower path, it'll record that, and it'll go a different way. So you can take all different kinds of patterns and find a path. So let's do this let's do Google Maps, but in a simpler form, and that's called maze traversal. Here I've got a really simple, think about a really simple like corn maze. And we're going to represent the corn maze like with ones and zeros, where ones is a path and zeros is a wall. So I'm going to start my maze traversal here at the upper left-hand corner, and I want to follow a path till I get down to the bottom right-hand corner. We are going to do this using recursion. So you can see the different paths out of here. And the goal is, once I find a path out of here, I will mark that with 7s. I will also mark what we see right here was a tried and path. So we'll be able to mark, as we go through this map, we'll be able to mark the places that we tried but failed, and we'll be able to mark the final path with 7s, saying this is the path you need to take to get out of the maze. So what you'll find is that if you start following the paths using certain algorithms, you'll find dead ends. I can travel down a path, like say for example, right off the bat. If I went down, starting from the top, I'm going to hit a dead end. If I went over here, I started going down. If I kept going to these ones over here, I can go up and around, and I'll hit this point where it's a dead end. So essentially what we're going to do is use recursion to find our way out of a maze. So here's the main function, and I'm going to start off by calling traverse. I'm going to create a maze and start traversing at 0, 0, which is the first of my two-dimensional array here. Okay, here's the recursive function, and it's going to look kind of weird because when you're thinking about recursion, you're going to actually assume the best case. We're going to start off by saying false. This function will return false if the path that it's following has a dead end. Okay, so that's what this Boolean traverse is going to do. If the path has a dead end, it'll return false. Now, if I go through the whole thing and the whole thing returns a false, hopefully if I go through this, I'll find a path and this will return true. If this returns true, I will know that the maze is solved because I'm down a path that is successful to get out of the maze. So starting right out, let's take a look at this and see how it's done. We won't expect you to do this, but it's good practice to see how this is working. We're going to assume that it's a bad path, so we'll start off by setting done to false. Then we're going to say, is this a valid coordinate point? Now, because we're going to check the path from every coordinate point, we're going to go down the path to the bottom, we're going to go to the left, we're going to the right, and to the top. So necessarily, I could get some of these coordinate points may be negative. I may put -1, 1. Well, what valid does is it makes sure that the row and column, the coordinate points I pass, are valid. So that's what it's doing here. I just moved to valid. Here you can say if I'm on the path, if I haven't gone too far to the right or too far to the left, or I'm off the path, then I'm still on the grid. And if I check my current coordinate point and if it's 1, I'm on the path. If it's 0, I've hit a dead end and I'm done. So if I'm on the grid and then I'm a 1, I know I'm going to return true, saying yes, this is a valid path I can follow. Alright, now that we've kind of gone over valid, if this is a coordinate point that's still on a path, it's still valid, I'm going to continue on. Otherwise, I'm going to return early. That's what this return false does. Anytime you see a return false in the middle of a method, no matter where you are, you're going to not do anything below it and return early. You will never hit this point right here. Okay, so now we have the grid, and we're going to mark it as tried. So we're going to put a 3 here. So we know that this is a valid path. We're going to put a 3 there to say, hey, we're trying this path. All right. Now at this point, we're going to take our base case. What is our base case? Well, our base case is we're done. We're all the way down at the lower right hand corner. We've finished. And that's what this is checking here, row and column. If we're down at the lower right hand column, return true because we are done. This is a valid path. Otherwise, we're going to check each other path recursively. So I'm going to follow the path down from wherever my point is on the maze. I'm going to search the path down. If I search the path down and it returns back true, I know that I'm on a good path that leads out of the maze. I'm done. I don't have to do these anymore. You see these not dones. Otherwise, if when I search down it doesn't find a good path, I'm going to try the path to the right. So here I am taking the path plus the coordinate point to my right. If that's successful, I'll return and I don't have to do any of these other paths. I know that I'm done. Otherwise, I'm going to try from my coordinate point up. So I'm going to go wherever I'm at, I'm going to the coordinate point just above me. If that works, if that doesn't work, then I'll try it to the left. If none of these work, done will still be false, and I'll return false, saying that I've tried, from my point, I've hit a dead end. I've tried all coordinate points around me, and it's false. However, if I found a good path somewhere along this line, I know that the current coordinate point I'm sitting on right now is a valid path. I'm going to change it. Instead of saying tried, which is 3, remember this 3 up here, that we set it to 3, I'm going to say I'm on 7. I'm going to set it to 7. Say this is a valid path, and I'm done. All right, that's essentially the program. We're going to recursively solve this problem. So let's kind of display how that works. Okay, so it solved it. Here's the grid before I go down the path. Okay, so all the ones and zeros. You can see what it did, what the algorithm did. You can see at first it went down. The first thing that it does in this function is go down in this traverse. So it starts at coordinate point 0, 0, and it goes down. I think the first, yeah, so we search down first. It goes down here and tries this coordinate point. Unfortunately, it hits all zeros and a 7, so it knows that it's a dead end. So it recursively ends that path, goes back up to the beginning. Now it's going to search right. You can see the 7s all follow the path all the way out of the maze. So here we go. I'm following it with my cursor here. You follow it all the way out, go down, up, left, down, and right, and you're out. You can tell by the 3s which path it tried but failed. It kind of hit a dead end. So if we follow it around, let's see, right here, I went 7s down and across. Now note, because it found a valid path going down, it didn't try this path up here to the top. So that's why it's still 1s, because the computer didn't need to go on the path on the top. It went down and found a valid path recursively. Went to left to the right here, and right about here you can see that it went down first, found a 0, then the next step is it went to the right. And you can follow it using 3s. It went to the right, down, right, up, left, up, and uh-oh, it hit a dead end right here. So it fell all the way back and went to the left. You can tell with the 1s and 3s which paths it tried and failed, or which paths it didn't even try at all. Okay, so let's go on to another puzzle called the Towers of Hanoi. This is another famous puzzle. If you played video games before, probably like role-playing games or whatever, like Knights of the Old Republic, they have similar games like this where you have to solve a puzzle called the Towers of Hanoi. Essentially, you have different sized discs on 3 pegs. The goal is to move the entire tower from one peg to the other. Each discs are different size, with the largest disc on the bottom and the smallest disc on the top. The rules of the game are you can only move one disc at a time. So you can't place a larger disc on top of a smaller disc. And all discs must be on a peg unless it is moving. So essentially the goal is, here's a picture of something of a real life Tower of Hanoi. So you want to move this entire tower from here over to here. And you have an extra stick here to help transfer things over. So you'll find yourself transferring things over to a temporary stick, moving the next disk over, transferring the peg back. There's an algorithm written that you can write in Java, and this is kind of how it's really simple. It's the process is very complex, but the way to solve it recursively is very simple. So we're going to weight the disks. So in this example, we're going to weight the disks 0 through 5, where the 0 is the smallest disk and 5 is the largest disk. We're going to call peg A, the first peg to the left, the start disk, the start. We're going to call the end the middle peg, and temp will be the third peg for now to start off with. So again, we got 3 pegs: the starting and the ending and the temp. Now, as we go through this, the start and the end, the temp tag, are going to change. Sometimes this will be the temp peg, sometimes this will be the temp peg, depending on what we are trying to do, which disk we're trying to move. So the simplest case is our base case. If the disk is 0, move it. We don't need to have any temporary peg. We just move it from the starting peg to the end peg, and that's it. Otherwise, if we are moving any other disk, we're going to move the tower. So move the tower above that disk from the start location to the temp location. So we're moving it out of the way. We're moving the tower above this disk out of the way. We're going to move that disk from wherever we wanted to start to wherever we wanted it to end. And then we're going to move that tower back to where we started. So essentially we're just moving a disk from one place to the other by moving the tower above it off to a temporary location and moving it back. Now this is fairly complex, but it's really cool. They have a website here that kind of goes through it, which has this algorithm here. It's not in Java, but it's very similar. So again, they have 0 through 5 disks. They've weighted them. The 5 is the biggest, 0 is the smallest. And they have pegs A, B, and C. So the goal is to move this whole tower from A to B. So starting off, you call the function, I want to move tower 5. I want to move you say the entire tower starts with 5 all the way up to 0. I want to move this from peg A to peg B. And the spare or the temporary peg that we can use is C. So I'm going to step into that, and the first thing is well, I'm moving tower 5, so I'm going to need to move tower 4. Someone would need to move everything over here over to C. So from A to C, you can see right here I'm moving all of tower 4 from A to C, using B as my temporary location. Taking another step in. Now that we have 3 over here, I need to move tower 3 off of 4 so I can move 4. So I'm going to move that from A to B, using C as my temporary. So you can see as I keep going into this, I'm keep calling move tower. I'm stacking this on top of each other. Finally, I'm to 0. 0 will move. So I'm moving it from A to C. I'm going to move it from A to C. Now I'm going to start popping things off the stack. Now I'm going to move, now that 1's clear, I'm going to move it from A to B. Alright. Now I'm going to pop that onto the stack. Now I need to move 0 from C to B, because I need to move 2 over here. Okay. Now that that's done, I'm going to pop this off. Pop this off, and now I can move 2 over here. Okay. Now I need to move 3, but I can't put 3 on top of 0 or 2, so I'm going to need to move all of this over into one tower so that I can move 3 onto B. Here we go. Now I'm going to move 0, 1. I'm going to speed this up. You get the idea. You can see how it's popping things on and off the stack. And we're slowly moving the tower over. So now I've moved 4 over. Again, I'm always putting a smaller one on top of a larger one. Alright, so now I'm finally moved tower 4 from A to C by swapping things back and forth. Now I can move 5 over to B. And I've finally got the base where I need it to be. I'll keep running this, and we're going to see how we move 4 back onto the stack. Alright, we're going to uncover 4 here soon. Okay, 4 is uncovered. 4 will then pop over. Now I need to uncover 3 and put 3 onto 4. Okay, done. Now I need to uncover 2 and put 2 onto 3. Uncovered 1, 0. Pop everything off the stack, and we're done. That concludes this video on recursion. Thanks for watching.